Hi, everyone. Thanks for being here today. I'm Scott Freitas, and today I'm going to be talking about evaluating graph vulnerability and robustness using Tiger. This is a collaboration between myself, Diyi, Srijan Kumar, Hanghang Tong, and Polo Chau. All right, let's get started. So let's talk a little bit of high level what Tiger is. So Tiger is a GPU accelerated Python library, and it's part of the NVIDIA Data Science Teaching Kit. So there's four major things that Tiger can do. So the first one here is it can quantify network vulnerability and robustness. Two, it can simulate a variety of network attacks, cascading failures, and the spread dissemination of entities. And then third, it can augment a network structure to resist attacks and recover from failure. And then finally, it can regulate the dissemination of entities on a network, such as virus or propaganda. And this presentation, we're going to go over each of these 4 points and give some examples of how Tiger can do these different aspects. And the toolbox itself can be found on github.com/Freita1/Tiger. All right, let's dive into it. What is network robustness and why should we study it? So we define robustness as a measure of network's ability to continue functioning when part of the network is either naturally damaged by singular cascading failures or targeted attacks. So we can see this on the figure on the right here, where we see a power transmission grid. And on the left side of this figure, we can see that maybe there's a malicious hacker who's attempting to take down some of the substations. And this could, maybe he successfully takes one down, and this could lead to some cascading failures leading to blackouts or brownouts across the Western coast. Alternatively, we could see that on the bottom right here in maybe Florida region, it could be impacted by something like a hurricane, where some substations are randomly taken down. And this could also lead to some cascading failures and blackouts. So essentially, by studying network robustness, we can measure and understand the network's robustness and its ability to defend and to resist these failures and attacks, and how to develop defenses to protect against them. So within the Tiger toolbox, we have 22 robustness measures. And these robustness measures can be broken down into 3 major categories: the graph, the adjacency matrix, and the Laplacian matrix. And so some of the things we've just been talking about were based on the graphs. We saw these nice pictures of the power transmission grid, the fiber optic networks, the water distribution networks. And we can look at things such as the vertex connectivity, the diameter, the average distance between the nodes. And these things have a very nice correlation with graph robustness. We can talk about some of this more in the paper. But at a high level here, we're just going to go over some of the things that are included. We also can look at things like the adjacency matrix of the graph, and including the Laplacian matrix also. So now we have some measures to study the vulnerability and robustness of these networks. We also want to look at the failure and attack mechanisms. So Tiger includes 17 failure and attack mechanisms, which is something that you can think of like networks suffer from natural failures and target attacks. We also talked about this in the power transmission grid. We'll also show an example here on the right on a water distribution network. So this here, we're using Tiger to simulate a node attack, we're attacking different pumps in the network, which are highlighted in red on the Kentucky KY2 water distribution network. And this is a simulated attack here. So in step 0 in purple here, we see the entire network is fully functional and operating. Then in step 13, we've targeted 13 of these sort of pumps for attack, and we can see in red they're now shut off. And this is separated the network into 2 different distinct groups, meaning the network is starting to disconnect and starting to fragment. We can see as this attack continues by step 22, the network is subdivided into 3 parts. And then by step 27, when only 27 of these pumps have been shut down, we can see the network has started to disintegrate, and it's now separated into 4 different components. We can see by the orange, the purple, the light blue, and the green. So this is one example of the kinds of attacks which you can do using Tiger. In addition, we've implemented 15 defense techniques. So these are kinds of techniques that can be used to defend against these attacks that we just talked about previously. However, it can also be used to defend against things like viruses and propaganda on networks. And here we're going to focus on Tiger defending against a sort of a SIS infection model, susceptible, infected, susceptible model, where viruses propagate on a network. On the top of the figure on the right, we can see the result of a virus that remains endemic on a network. when there's no defense. And on the bottom of this figure, we can see when we only defend 5 nodes using a method like net shield, we can eradicate the virus. So on the top here at time step 50, we can see at both the bottom and the top that the virus is proliferating across the network. And then by time step 150, the difference is still between the top and the bottom without defense and with defense respectively. This virus is still very prolific. And then finally at time step 1000, we can see by defending just 5 nodes in this network, we're able to eliminate a large majority of the virus, whilst without defense, it remains endemic in the network. So a little more in depth, we can give a nice example here of this identity dissemination, how it actually worked using Tiger. We can see we want to set up a couple parameters in this dictionary. So these are sort of the modeling parameters we want to pass. Then after we set the parameters, we load the graph by specifying one of the pre-load networks, or we can create our own custom network X graph. And then we feed this graph in along with the simulation parameters into the class diffusion itself. We run the simulation, and then we can generate these nice figures and videos here on the right. And here I'll play a quick example where we're going to see these 5 nodes defended in dark blue. And that we can see essentially what's happening here is that the virus is proliferating across the network, but over time it starts to decay. And then close to the end of the timestamp here, we can see that the virus begins to die off completely. And this is only with defending about 5 nodes of the network. So this gives us a nice little video example of what's happening. And you can create these videos directly using Tiger and running your own simulations on your own networks. So we've already alluded to one of the simulation techniques available within Tiger, the entity dissemination. However, also things like cascading failures that we can simulate, attacks, and defense scenarios. So another cool example here we can look at is cascading failure simulations on something like the US power grid when a couple of the substations are attacked. So below here is a representation of the US electrical grid. And we can see at time step 1, we can simulate different loads of the network indicated by the shades of blue. A heavier load in dark blue, a lighter blue indicates a lighter load. And we have different capacities represented by node size. And basically what we can see here is on the left is the network operating at regular. However, when 4 of these substations are attacked at random or by targeted attacks, in this case, we're looking at targeted attacks, we can see that the simulation here in the middle, that it started at the bottom, and that basically it started to proliferate, and this cascading failure went across the different substations and started to spread, taking down the whole electrical grid. And we can see by time step 70 over here on the right that these failures are trying to distribute the load from each of the nodes that are failing to other nodes in the network. And we can see the cascading failure occurring. So a nice advantage of this kind of setup here is that we only need to set up a few parameters in order to get the simulation to run. We can then specify the network X graph, either using one of the built-in ones or your own. And then we can pass these parameters into the cascading class itself, and then we can run the simulation. So we can do that here on the right. It's basically going to follow something very similar to what we saw below in the figures previously, where in this case, the failure stops in the top right. We can see that the load's being redistributed. However, the remaining nodes aren't able to handle the additional increased load, and they begin to fail. And we can see this leads to a cascading failure simulation across the network. Eventually, this will reach to a point where the whole network fails. So thanks for everyone for being here today. In summary, Tiger is a GPU accelerated Python library, and there's 4 major things which it can do. It can quantify network vulnerability and robustness. It can simulate a variety of network attacks, cascading failures, and spread dissemination entities. It can augment the network structure to resist these attacks and recover from failures. And then finally, we can regulate the dissemination of entities on these networks. All right, thanks everyone, bye.